To the Greeks, the circle was a symbol of the divine symmetry and balance in nature. Greek mathematicians were fascinated by the geometry of circles and explored their properties for centuries. Circles are still symbolically important today. They are often used to symbolize harmony and unity. That was a quote excerpt from an article by Jill Howard on the website enrich.math.org. So in this lesson, we will be continuing that culture of the Greeks by exploring the properties and theorems regarding the circle. But let's begin our study with a definition of the circle. A circle is a set of points, or what we call a locus, that are equidistant from a fixed point. The fixed point is called the center. The distance of each point in the locus from the center is called the radius. The distance, which is twice the length of the radius, is called the diameter. And the distance formed by all the points in the locus is called the circumference. So what does that look like? It looks like this. All right, and the locus would be all the points that go around and form what is called the circumference. The diameter is twice the radius, this length here, and then the radius, well, that is the fixed, that is the consistent distance between any point on the circumference and the center. So now we want to discuss the parts of the circle. So let us pay attention to this diagram and discuss the parts individually. So we have, first of all, the arc. The arc is a portion of the circumference. So remember, the circumference is just all these points that are part of a locus. It's a set of points, right? But you could think of it simply as the distance around the circle. Well, the arc is just a portion of that distance. Next, we have a chord. A chord is a line segment between 2 points on the circumference. And here is our chord on the diagram. You could clearly see it's a line between 2 points on the circumference. This will be 1 point, and this will be another. So it's important to note here that the diameter is the longest chord of a circle. As you can see, the diameter is from this point on the circumference, and the line goes across to this point on the circumference, right? And this qualifies as a chord based on the definition, and it is important to remember because it would help in solving some problems to know that the diameter is the longest possible chord you could get in any circle. Next, we have what is called a segment. That's the area between a chord and an arc. So here is the segment in the circle, and we call this in particular the minor segment because, of course, the area looks pretty small. So if there's a minor, there is a major, and that is this part of the circle that has been colored yellow, right? So remember, it's the area between a chord. We could clearly see the chord, and here is the arc. That is a segment, and for the major one, the chord will be this chord as well. The arc would be this entire distance here, right? So it's the area between those two things. And next we have the sector, which is just a part of the segment, right? It's the area between two radii and an arc. So here's one radius, and this is another radius, and here's an arc. So that is what we call the sector. The best way to remember it is just to think of it as a pizza slice, right? That is what a sector is. So next we have what is called a secant. That's a line intersecting the circle at 2 points, right? So here's our secant. You can imagine it as a long Japanese sword just slashing through or stabbing through the circle at 2 points, at the entry and at the exit. So this is called a secant. And another line external to the circle, we call this a tangent, and it's a line intersecting the circle at 1 point. So here is a tangent which just seems to graze past the circumference of the circle and actually graze and touch 1 point in particular. So these are the parts of the circle. All right, so what do we know so far? We know the definition of a circle, and we know its parts. Now it's time to discuss the theorems of the circle. And the theorems represent discoveries by those same Greeks and possibly other mathematicians. In the many years of exploring the circle, right, they would have discovered angles and how to derive the exact value of certain angles. All these discoveries were established by proof, which makes them theorems, right? They are small pockets of theory that has been established by proof. So let's look at them. First, we will just label them 1, 2, 3, 4 for identification purposes. Theorem 1 says angles in the same segment and standing on the same chord are always equal, right? So we know what a segment is, we know what a chord is. So here's the chord, and the segment would be this major segment here, and the two angles that has been subtended or created from that chord, right? Those two angles are equal, right? You could also think of these two angles as being standing on the same arc. This would be the arc, right? In some questions, they may not give you the chord, so it's important to note that the arc also works as a foundation from which to build these angles in a segment. So next we move to theorem 2, which says the angle at the center of a circle is twice the angle at the circumference. So what is the angle at the center? This is the angle at the center right here, all right? And that would be 2 times whatever this angle is. So in order to understand fully the setup, what you need to have is the angle at the center is subtended from a particular arc, this one, and then the angle at the circumference is subtended or created from the same arc. All right, so please observe that both angles have been created or subtended from the same arc. Once you have that kind of relationship, then there's another relationship which is also true, and that is that the angle at the center of the circle is twice the angle of the circumference. Next, we have in theorem 3, the angles in a semicircle is always 90 degrees. So a semicircle would always be, your chord will be your diameter, right? Remember, the diameter is the longest chord, and that would always give you half the circle. So if you subtend or create an angle from that chord, you will always get a 90-degree angle. So here in this diagram, we have 2 90-degree angles being formed, all right? So that's why they say the angle in a semicircle, in other words, an angle subtended from a diameter, would always be 90 degrees. And last but not least, right, there are actually 9 theorems of the circle. This lesson we will only look at 4. ABCD is a cyclic quadrilateral, right? A cyclic quadrilateral is a quadrilateral or 4-sided shape where each point touches the circumference. So please note that the points of the quadrilateral must touch the circumference, okay? So here we have A, D, C, B, right? Those points are touching the circumference. If I draw, for example, a square inside the circle and just 2 of the points on that square touch the circumference, and the others don't, then it's not a cyclic quadrilateral. It's just a quadrilateral. So, but once we have a cyclic quadrilateral and it meets the condition that all the points on that quadrilateral are touching the circumference, then here's what is true. All vertices lie on the circumference of the circle. Diagonally opposite angles add up to 180. So that is why angle D and angle B, right, if we add them, we will get 180 as suggested by this calculation here. And whatever angle C is and angle A is, right, they are diagonally opposite, just like D and B were. So whatever angle C is and whatever angle A is, when we add them up, we will get 180 degrees. 2 angles that add to 180 degrees, we have a mathematical term for them. We call them supplementary angles, right? 2 angles that add to 180 degrees, we call them supplementary angles. So here are the 4 theorems of the circle, 4 discoveries that Greeks and other mathematicians from other nations might have combined to discover and establish by proof. Now we will look at some problems where each theorem is applied to solve unknown angles. As a matter of fact, that is the practical use of the theorems. They are used to determine unknown angles within the circle. All right, and so what you would have generally is other geometric structures being superimposed on the circle, like for example these lines, and these lines would combine to create angles. You have little triangles, you have quadrilaterals, right? So once we superimpose other geometric structures on the circle, we have at our disposal 4 theorems which will enable us to determine unknown angles within that circle. So let's get some practice actually doing that. Here is problem 1. We are discussing now the applications of the theorem, and the question says, the data says A, B, C, and D are points on the circumference of a circle. The center is O. Chords A, B, and CD intersect at the point X. So they intersect here. This is the chord AB, and this is the chord CD. So more data tells us that angle AXD is 92 degrees, that's this angle here, and angle CBA is 57 degrees, that's this angle here. What is the size of angle DAX? Okay, so I'm just first of all gonna give you the answer. All right, the answer is B, 31 degrees. But to explain how we got there, right, we would first have to locate angle DAX. Where is angle DAX? It's this angle right here. Okay, the letter in the middle always kind of tells you where the angle is located, right? So DAX, it's this angle right here. But we can't get to it directly. Okay, what we would first do is work out angle ADX, right? So ADX is 57 degrees. How do I know that? Well, I applied theorem 1, which says angles in the same segment and standing on the same chord or arc are equal. So consider the arc AC, right? Or even better, just imagine a chord AC, like so. So this chord would actually subtend this angle here, right? Or create. And then this same chord would also create or subtend this angle here, 57 degrees. So what we have is the angle ABC or CBA, right, is 57 degrees, and therefore here would also be 57 degrees according to theorem 1. So on the strength of theorem 1, I am able to say that angle ADX is 57 degrees. Then I can continue with this calculation, angle DAX, which is what they want me to find, right? You see, because if you consider triangle ADX, right, there is the angle 92 degrees. We just worked out 57 degrees. So to find the third side, we apply the fact that the sum of angles in a triangle is 180 degrees. And so just add the two other known angles that we have. We will get 180 minus 149, and that works out to 31 degrees. Hence, our answer is B. All right, so this was an example of applying theorem 1 to derive or arrive at the value of an unknown angle, right, DAX. Okay, here's another problem, right? L, M, and N are points on the circumference of a circle with center O. Angle MON is 98 degrees, as we could see on the diagram. What is the size of angle MLN, right? Angle MLN is this angle right here. Okay, so I want you to pause the video and just consider this problem for a bit and see if you could work out the size of angle MLN. Okay, pause the video now. Okay, for those of you that got B as the answer, congratulations, you are a brilliant solver of unknown angles in the circle. All right, and the explanation for B being, sorry, the angle MLN being 49 degrees, well, remember this theorem that says the angle at the center of a circle is twice the angle at the circumference or outer edge. So what is the angle in the center of the circle? It's 98 degrees, and we could verify that that angle was subtended from the arc MN. Well, another angle that was subtended from that same arc MN is this one here. So we have all the conditions in place to apply theorem 2. So the angle here would just be half of 98, right, as suggested by this calculation, which is 49 degrees. So B is your answer. All right, kudos to those who got this right. Here is a third problem. It says AB is a diameter of a circle, center O. C is a point on the circumference of the circle such that angle CAB, right, that is this angle here, is 26 degrees. What is the size of angle CBA? Pause the video and try to work that angle out. Pause the video now. Congratulations to all those who selected C as your answer. You are doing quite well in this lesson, and I have no fears for you in terms of understanding subsequent lessons in this topic. Right? Why is the answer C 64 degrees? Well, here we apply theorem 3, which says angles in a semicircle is always 90 degrees. So that's why we have this 90-degree angle here. All right? Remember, diameter, any angle subtended from that diameter is considered to be an angle in the semicircle, and that will always be 90 degrees. So we have 90, we have 26, we add those two and subtract it from 180 to get 64. So C is our answer. All right, excellent work from those who would have at least even attempted this and got it right. And finally, we have problem 4. ABCD is a cyclic quadrilateral drawn inside a circle center O. Angle ABC is 108 degrees. What is the size of angle ADC? All right, so angle ADC is this one right here. Pause the video. Again, I know I'm making you pause the video a couple times, right? But it's just to give you a chance to, make an attempt, right? Because when you attempt things, even if you get it wrong, that's how learning happens. All right, so don't be afraid to get it wrong, but work out, at least try. So, and if you get it wrong, you will see why, and you would also learn from that. So, just take heart in the opportunity to learn. So go ahead and pause the video now. Okay, congratulations to those that got this right, because the answer is A. And for those of us that just want to enjoy the show, let's see the explanation for why 72 degrees is the size of angle ADC. Well, ADC is 180 minus angle ABC. Why can I say that? Because of theorem 4, which says the opposite angles, and more specifically the diagonally opposite angles, all right, B and D, angle B and D are opposite angles of a cyclic quadrilateral. Is it a cyclic quadrilateral? Well, all 4 points on the quadrilateral are touching the circumference, so yes, it is a cyclic quadrilateral. So theorem 4 says opposite angles of a cyclic quadrilateral are supplementary, meaning that they add up to 180. So that is the reason for this calculation. 180 minus 108, which was the size given for angle ABC, that will work out to 72 degrees, and hence A is our answer. Okay, so this brings us to the conclusion of this lesson, circle geometry theory, part 1. Okay, we discussed only 4 theorems basically, and we saw how they are used to determine unknown angles in circle problems. We also learned the definition of a circle and the different parts of a circle. Those things are extremely important, because when reading questions like this one, ABCD is a cyclic quadrilateral. You have to know what that is. You have to know what things like what the center of a circle is, what is a radius, diameter. Okay, so all of that was covered in this lesson. So stay tuned for the next lesson, which is Circle Geometry Theory Part 2. In that lesson, we will look at the other theorems, the other discoveries that are used to determine unknown angles in circle problems. So stay tuned, and in the meantime, may the math force be with you.